Welcome back. Today, we were diving into fascinating topic that lies at the very heart of everything we study and explore, which is the nature of mathematics. Mathematics isn't just about the numbers, equation, or algorithms. It is a universal language that helps us to understand the world around us, from the patterns in nature to the logic that drives our technology. That is, math is everywhere, influencing how we perceive reality itself. In this lesson, we're going to explore what makes mathematics so fundamental, how it shapes our thinking, and why it's considered one of the most powerful tools in humanity has ever developed. Whether you are a math enthusiast or someone who struggled with it in the past, this video will give you a fresh perspective on why math is not just a subject in school, but a way of understanding life. So, let's get started. So here there is the types of pattern in nature, which is the symmetry. And symmetry is when different sides of some things are alike. We have similarity by the means of this reflection may be a mirror image when only two sides like two sides of our bodies. They may be symmetrical on several sides. And we have different types of symmetry, particularly with the patterns in nature. So now let us have with bilateral or what we call mirror symmetry. Bilateral symmetry is a symmetry with respect to reflection, which is this is a type of symmetry where an object can be divided into two identical halves along a single plane. Imagine drawing a line down the middle of a butterfly's body. Each half would be a mirror image of the other. So, this type of symmetry is common in nature and is often seen in animals. Like, for example, you have seen in our given example pictures, including humans, where the left and the right sides of of the body are symmetrical. It is like folding a piece of paper in half, both sides match perfectly. Another types of symmetry is rotational symmetry or radial symmetry. It is also found at different scales among non-living things, including the crown shape, splash pattern formed when a drop falls into a pond. Rotational symmetry is occurs when an object can be rotated around a central point and still look the same at various angles. Like for example, when a drop of water falls into a pond, it creates ripples that spreads out in circle from the point of our impact. So this is a perfect example of radial symmetry. If you look at the ripples from above, you will see that they are circular and evenly spaced around the center where the drop fell. So no matter how you rotate the image, like for example here, the pattern of ripples will look the same, which is a hallmark of radial symmetry. The ripples expand outward in all directions, maintaining their symmetry as they move across the surface of the water. Another type of symmetry is we also have fivefold symmetry, which is also known as the pentagonal symmetry. So it occurs when an object can be divided into five equal parts that they are identical in shape and size, with each part being a mirror image of others when rotated around a central point. So it is found in the group of include starfish, sea urchins, and sea lilies. So this type of symmetry is less common in nature compared to bilateral or radial symmetry. A classic example of fivefold symmetry is a starfish, particularly one with five arms. No matter how you rotate the starfish by 72 degrees, which is 360 divided by 5, that is 72, it will always look the same. So this symmetry is also seen in flowers like the common daisy or in the arrangement of seeds in our pomegranate. So um, fivefold symmetry is unique because it doesn't easily fit into the more common symmetrical categories like bilateral or simple rotational symmetry, and it making it especially interesting in the study of natural patterns. And of course, we have five-fold symmetry. We also have six-fold symmetry, which is each flake structures forming a record of the varying conditions during its crystallizations. Six-fold symmetry is also known as hexagonal symmetry when occurs when an object can be divided into six identical parts around a central point. So just like, for example, in five-fold symmetry, here in six-fold symmetry, if we rotate the object by 60 degrees, it will still look the same. Okay, so this type of symmetry is commonly found in nature and is particularly notable structure like snowflakes and honeycombs. So for example, a snowflake has six arms that radiate from a central point. So each one being a mirror image of the others. So no matter how you rotate the snowflake by 60 degrees, it retains its shape and pattern similar. And then the hexagonal cells of a honeycomb exhibit six-fold symmetry, where each cell fits perfectly with its neighbors, forming a strong and efficient structures. So six-fold symmetry is just a fascinating because it's both aesthetically pleasing and functionality efficient, which is why it's often seen in natural formations. While we have fractals. Fractals is these are infinitely self-similar, iterated mathematical construct that having fractal dimensions. Fractals, these are complex geometric shapes that exhibit self-similarity, as we said, meaning they look similar at different scales. If you zoom in one small part of a fractal, you will find that it resembles the whole shape. This property is what makes fractals unique and visually fascinating. Fractals can be found both in nature and in mathematical construct. For example, consider the branching patterns of a tree. Each branch resembles the entire tree, and even the smaller twigs mimic the larger branches. So similarly, coastlines, clouds, mountains, ranges, and certain types of ferns display fractals-like patterns. In mathematics, a well-known fractal is the Mandelbrot set, which is created by iterating a simple mathematical equation. When you zoom in on the different parts of the Mandelbrot set, new and integrate patterns emerge, so each resembling the overall shape that we have. Fractals are used in various fields, from computer graphics to modeling natural phenomena, because they can describe complex, irregular shapes in a simple way. Their definite complexity and self-similarity make them a fascinating subject of the study in both art and science. Now we have spiral. Spiral is a curve which emanates from a point moving farther away as it revolves around the point. So as we said, it is a curve that starts or it has a point at or what we call central points and winds outward in a circular pattern. It can be seen in many natural objects like snail shells, the swirling pattern of our galaxy, or the arrangement of sunflower seeds. Spiral can either have evenly spaced loops like spring or get wider as they go out. Like we said earlier, the snail shell. So this shape is common in nature because it efficiently packs or spreads things out. So that is spiral. When we say tessellations class, these are the patterns formed by repeating tiles all over a flat surface. So this pattern made up of shapes that fit together perfectly without any gaps or overlaps. So think of it like a tile floor where each tile snugly fits against its neighbor. Tessellation often use simple shapes such as squares, we have triangles or hexagons that repeat in a regular, orderly way. So you will find tessellation in various places from honeycombs in nature to intricate patterns in art and designs. So essentially, tessellation creates a visually appealing and efficient way to cover a surface. Just like, for example, we have picture here in our PowerPoint. And bubbles is a soap bubble from a sphere, a surface with minimal area. So bubbles is just like a thin sphere of liquid filled with air or gas. So they form when a salt film traps a layer of air between the two thin layers of our liquid. So creating a spherical shape due to surface tension, these tensions makes our bubbles stable and allows them to float. So in simpler terms, if you were to look at a bubble from any angle, its surface would appear uniform because it shapes like a perfect sphere. So this symmetry is intrinsic to sphere and is specific type of radial symmetry, where the symmetry is uniform in all directions around a central point. Another types of pattern in our symmetry, we have stripes. So these patterns have an evolutionary explanation. So stripes are long, narrow bands or lines that runs parallel to each other. So differing in color, width, or textures. They can appear in variety of patterns and are commonly used in fashion, designs, and nature. Stripes can be vertical, it can be horizontal, it can be diagonal, and their arrangement can create different visual effects. So, example of stripes, like for example in our fashion, striped clothing such as shirt and dresses where stripes can vary in width and in color. In a design, patterns on a wallpaper, rugs, or curtains, we use stripes to add visual interest. And while in our nature, stripes on animals like zebras or tigers, which often serve as camouflage or as means of their identification. So in terms of symmetry, stripes can exhibit translational symmetry when the pattern repeats at regular interval. So if the stripes are evenly spaced and consistent, moving the pattern along the lines of stripes does not change its appearance. Now let us have with cracks. Okay, so cracks are linear openings that form in material to relieve stress. So thus the pattern of cracks indicates whether the material is elastic or not. So when we say cracks class in the patterns in nature, so cracks are fractures or it's like a splits that appear on a surface. Typically due to the stress or pressure or changes in temperature, they can be vary in size, depth, and pattern, and they often indicate underlying problems or weaknesses in the material. So example of that is in concrete. We have cracks in a sidewalks, roads, or building foundation caused by settling, temperature changes, or structural stress. In glass, we have the cracks in a window or screens resulting from impact or stress. However, in some cases, such as with certain types of geologic cracks or cracks that form under specific conditions, they may be patterns or recurring features that show some degree of symmetry or structure. So now, let us have with our lesson number 2. So Fibonacci sequence. So when we say sequence class, it is an ordered list of numbers called terms that may have repeated values. So particularly with this topic, Fibonacci sequence, this is a series of numbers where each number is the sum of the two preceding ones. And always remember this class, or take note of this, that we can say a given series of number is a Fibonacci if it started from 0 and 1. So the sequence begins as follow. Like for example, 0, 1, 1, 2, 5, 8, 13, 21, and so on. And as you observe, we add the two preceding numbers, right? Or we get the sum of the two preceding ones, which is for us to have the present number. So each number in the sequence is found by adding the two previous numbers together. So a sequence, as we said, by this Fibonacci sequence, so each element follow up a specific pattern or rule, which is called term. So that's how Fibonacci sequence process, which is uh, we add two previous numbers for us to have our present number. So that is Fibonacci. So now let us have an example of that. So let Fibonacci sequence be the nth term of the Fibonacci sequence. So with Fibonacci sequence 1 is equal to 1, Fibonacci sequence 2 is equal to 1, and Fibonacci sequence 3 is equal to 2, and so on. So the things that we are going to look here is to find the Fibonacci sequence 8. As we remember, I mentioned to you wherein we added the two previous numbers together for us to have the present number. So for us to find out the Fibonacci sequence 8, let us uh, rewrite what is given in our problem. So it says here our Fibonacci sequence 1, or the first term is 1. The second is 1. So the third term is 2. So therefore, by finding that, in the process of our Fibonacci sequence, we added the two previous number, which is 1 plus 1. So we will have 2 for that, and that will be our third term. So now for our Fibonacci sequence 4, we have 2 plus 1. So added by the previous number, so we will have 3. For our Fibonacci sequence 5, so added the two previous number again, so we will have 5. So in 6 sequence, so we have 3 plus 5, we will have 8. And then continuous process, adding the previous two numbers, we will have 13. And now, finding the Fibonacci sequence 8, 8 plus 13, we will have 21. So therefore, Fibonacci sequence 8 is equal to 21. Okay, so let us have another example. So if Fibonacci sequence 22 is equal to 17,711 and Fibonacci sequence 24 is equal to 46,368. So what is Fibonacci sequence 23? So as we remember, by adding the two previous number, we will have our present number. So as our solution, we can identify our value of Fibonacci sequence 3 by letting this kind of equation. So we have Fibonacci sequence 22 plus Fibonacci sequence 23. As we all know, by adding these two numbers, we will have Fibonacci sequence 24. So now let's just substitute our given value, which is 17,711 plus the Fibonacci sequence 23, which is we are looking for, and that is equal to 46,368. So as you can see, we can use here the property of equality by subtracting 17,711 to 46,368. So now we will have 46,368 minus 17,711, and that is 28,657. Okay, so I hope we are clear with this. And then we are going to another example. So let us evaluate these given equations. So Fibonacci sequence 1 plus 3, Fibonacci sequence 4. As we all know, we have a given sequence which is 1, 1, 2, and 3. And we identify that Fibonacci sequence 1 is equal to 1 and Fibonacci sequence 4 is equal to 3. So let us just substitute those values in our given. So 1 plus 3 times 3 because our Fibonacci sequence 4 is 3. So simplifying this, we will have 10. 1 plus, okay, so 3 times 3, that is 9. So plus 1, that is 10. So that's how the process we simplify a given Fibonacci sequence and to identify their sequence of number. So now let us dive into arithmetic sequence. So arithmetic sequences follow a pattern of adding a fixed amount from one term to the next. So we're in arithmetic sequence is a sequence of number in which the difference between any two consecutive terms is constant. So this constant difference is known as the common difference. So as you can see, we have a general formula to get the arithmetic sequence or to use. We are going to use in arithmetic sequence, we have the a sub n is equal to a sub 1 plus the quantity n minus 1 times t. Wherein our a sub n, that will be our n term, and a sub 1 is our first term, and our d is the common difference, and our n is the term number. So when we heard common difference or the word difference, that it means that we are going to use operation of subtraction. Okay, so let us have an example for us to have a clear understanding on how we're going to use this formula in arithmetic sequence. So let us find the 14th term of arithmetic sequence 5, 7, 9, and then 11. So we are looking for the 14th term. Okay, so for that term that we have, so let us just rewrite our formula. A sub n is equal to a sub 1 plus the quantity n minus 1 times d. So as we remember, our a sub 1 is our first term. So what is our first term here? So that is 5. So now, our n here, which is the term number. So what is our term number? That is 14. Okay? So now let us find their common difference. So we can find that by subtracting the previous number. So we have 7 minus 5, so that is 2. Either of the term number, we are going 9 minus 7, that is 2. 11 minus 9, the difference is 2. That is why they called common difference, because they have a common difference. Okay? So let us just substitute because we already have our given values. So substituting all those value for the value of n, that is a sub 14. So we will have for a sub 1 is 5, and then our n is 14, and then our common difference is 2. So to simplify this, let us take first the inside value in the parentheses. So 14 minus 1, we will have 13. And then multiply it by 2, which is we are following the process of PEMDAS, which is parentheses, exponent, multiplication, division, addition, and then subtractions. Now we have right now 5 plus 26. So now this will be our a sub 14, which is equal to 31. So that will be the 14th term that we are looking for. So that is equal to 31. So now let us have another example. So in the arithmetic sequence, -7, -4, -1, and then +2, and so on. What term is 44? So now, let us just rewrite our formula for us to find out what we're going to look for. So first, we are looking for the term. So remember, our n is equal to the term number. So we are looking for our n here. But right now, 44 is our a sub n. And then our first term is -7, which is the a sub 1. And their common difference, that is equal to +3. So remember, negative 4 subtracted negative 7, so we have positive 3. Okay, so now let us just substitute those value in our given formula. So our a sub n is 44, a sub 1 is negative 7, plus 3. So our n, so that is the things that we are looking, the term number, minus 1. Okay, so now let us just use distributive property to simplify this. So 3 multiplied by n, it will be 3n. And then 3 multiplied by negative 1, it will be my negative 3. So that is why we have 44 is equal to negative 7 plus 3n minus 3. Okay, so now simplifying this, um, using proper type equality again. So let us just add 7 and then add 3 on both sides. So we will have 44 plus 7 plus 3. Okay, and that is equal to 3n. So simplifying this, 44 plus 7 plus 3, that is equal to 54. And that is equal to 3n. So simplifying this, divided by both sides by 3, we will have our n, which is coming from the 54 divided by 3, that is equal to 18. So that is the term that we have, which is 18. Now let us have with geometric sequence. A geometric sequences or geometric progression is a sequence of numbers where each successive number is the product of the previous number and the some constant r, which is our common ratio, wherein we are using the general formula of a sub n is equal to a sub 1 times r raised to n minus 1, wherein a sub n, that will be our n term, and the same thing in we did earlier with our arithmetic sequence. The first term is a sub 1. Now we have our r, which is the common ratio, and n is our term number. Now for us to have a broad idea about how to use the general formula of geometric sequence, let us have an example. So find the 10th term of the geometric sequence 3, 6, 12, 24, and then 48. So rewriting our general formula for that, we have a sub n is equal to a sub 1 times r raised to n minus 1, which is our first term here is 3, and then our term number, that is 10. And to get the common ratio, that is 6 divided by 3, that is equal to 2. Wherein the second term divided by the first term, we will get the common ratio. Either of the term that we are going to, for example, where we want to get the ratio of 48 divided by 24, that is also 2. That is why they are called common ratio. They have a common ratio, which is 2. Now we all have those value. We are going to substitute that in our general formula. So we have a sub 10 is equal to 3 times 2 raised to 10 minus 1. So simplifying that, 10 minus 1 as our exponent, that will be 9. So now we have 3 times 2 raised to 9. So 2 raised to 9, that is equal to 512. So 512 times 3, that is 1,536. Wherein that is the 10th term of our geometric sequence. I hope this lesson has given you a new perspective on how mathematics shapes and connects with various aspects of our lives. If you enjoyed this video, don't forget to give us a thumbs up and subscribe to the channel for more insightful lessons. So feel free to leave any questions or thoughts in the comments below. I'd like to hear how math has impacted your life or any topics you'd like us to cover next. So thank you for watching, and I'll see you in the next video.